Next on the agenda, we have friction. And this deserves its own video because this is where things start to get trickier in the forces unit. And so we start with the force of friction being that it's a force that opposes the direction of motion. So if your object is moving to the right, that means the force of friction will act to the left. Versus if your object is moving to the left, then the force of friction will move to the right. Okay? So it always goes against the direction of motion. And it's given by this equation, F of F. So this little F over here stands for friction, is equal to mu times F of N. So this mu is a Greek letter. It stands for the coefficient of friction. And this over here, this other force, is the normal force. So you definitely need to know and look back to the other video to see what normal force is. Remember and recall that it's the force, a reaction force from the surface in response to a force applied to that surface. So if you have a weight resting on a surface, then in response to that, the normal force will push back up on the object, equal and opposite to the weight. There's something called drag force, and it's a type of friction force for motion through liquids and gases, but the type of friction we're going to look at for the most part is in contact with surfaces, surface friction, not really drag force. But that's also good to know, some fun thing to know. And when you have friction, heat energy typically accompanies that, and that's important for later on when we talk about energy. So I have to talk about the coefficient of friction, mu. So oopsies, it's kind of covered over here, so mu. And this table right here is taken directly from the Regents reference table. And it gives you the values of the different coefficients of friction between two different surfaces. So this coefficient is dependent on the two types of surfaces in contact with each other. And you can see there are two types, static and kinetic. So static meaning at rest, when the object's at rest, and kinetic is when the object is in motion. Okay? And if you can see here, the kinetic friction is smaller than the static friction. Static friction is greater, and why is it greater? Because it takes more force to overcome the static friction than you would kinetic friction. It takes more force to get objects to start moving than to keep it in motion. So if you think about pushing heavy objects, it's always harder to get it to start moving, and then once you have it in motion, it's not that bad. You don't require as much force than you did before. And if you notice, there are no units, and they're all decimals below 1.0. So the higher the coefficient, closer to 1, the higher the friction. So this is sort of meant to represent a sort of certain percentage, I guess. When tackling friction problems, it's important to draw free body diagrams, because you're definitely going to need to remember all the forces in play. So we have an object on a surface, its weight will always push down. In response to that, the normal force will push back up from the surface. We typically take our applied force to the right, and so the force of friction will be opposite that, going to the left. And you definitely need to identify keywords to see if the object is in equilibrium. That means either at rest or constant velocity. This one, the third one, I can't stress anymore. Remember that F of N, the normal force, is equal to the weight of the object unless stated otherwise. So these two forces are equal but opposite. So by finding the weight, you get the normal force as well. It's also important to remember the difference between static and kinetic friction. So sometimes they might give you two different values. You need to know whether or not static is being used or kinetic is being used. And it depends whether or not the object's at rest or moving already. And so this leads us into the two different scenarios where you don't have acceleration and when you do have acceleration. And so when you don't have acceleration, that means your net force is 0. The object's in equilibrium. And so our free body diagram is going to show that all these forces are balanced out. So these two important forces are equal but opposite. Okay? Now on the other hand, if you do have an acceleration, that means your net force is not 0. That means you have a number that's not 0. That means it typically indicates that the force is greater than the force of friction unless it's slowing down. So there's an imbalance in our scenario. So the force of friction is not equal to the force. That means you need to use F net equals MA to figure out what's that net force, so you can figure out the differences between the left and the right sides. Okay? And so here I'm going to go over a simpler example where you're just using this equation, F of F equals mu times F of N. This is on the simpler side, which requires the use of the reference table though. So you have to find the force of friction acting on a 30 Newton rubber box sliding on wet concrete. So rubber on wet concrete. So that means we need to look at our reference table and right here. So it's sliding already. That means we're using this guy, the kinetic coefficient of friction. Looking for F of F. We have the mu equals 0.58. Now, do we have the normal force? They gave us 30 newtons to describe the box. 30 newtons, newtons being a force, so this is the weight. If they give it to you in kilograms, you need to convert that mass into a weight. So this is the weight of the object in newtons. And remember that the weight is equal to the normal force. That's what you need to remember. So that we have everything we need. Equals 0.58 times 30 newtons. Multiply them together and you get your answer. And the answer is 17.4 newtons. Now here we have a much more difficult problem that should be broken down into steps, but in this problem, it's not broken down into many parts. You need to take all these steps to get to the final answer. And what it's looking for is the coefficient of friction. So we're looking for mu. That we don't have. They gave us a horizontal force of 30 newtons. That means the force you're applying is 30 newtons. You're sliding a 12 kilogram crate, so the mass is 12 kilograms. And it's moving with constant velocity. So when we draw a free body diagram, our force is 30 newtons. We have a force of friction to the left. The weight of the object goes down and the normal force pushes back up. So that means when you're at constant velocity, this is in equilibrium. So this right here indicates equilibrium. So that means this here is also 30 newtons. Alright? Now, they didn't give us the weight, but they did give us the mass. So we need to take this extra step of converting mass into newtons. 12 kilograms times 9.81, because we're assuming we're on Earth. And this will give us 117.72 newtons for the weight. Now remember, the weight is also the same as the normal force. Okay? And so looking at our equation for the force of friction, this is the only equation that has mu. We have our force of friction, that is 30 newtons. The mu is what we're looking for, and the normal force we just got as 117.72 newtons. So dividing both sides by 117.72, you could get your mu, and it is 0.25. no units, and that's it. Now, in the case that they give you an acceleration, then you need to take that mass times acceleration to figure out the net force. So that could give you the difference between both the left and the right sides. And once you figure out which one is the stronger side, you can figure out what's the weaker side then. And that's it. So stay tuned for the inclines and pulleys video as well as the 2D statics for the honors class.